So I want you to imagine standing next to a machine that is 220 meters long.
Which is just, I mean, it's hard to even picture.
Right. To put that in perspective for you, you are looking at something the length of more than 2 full football fields, just, roaming across the earth.
Yeah, specifically in Germany's Hambach mine.
Exactly. And it weighs 14,200 metric tons. This is the Bagger 293, the largest land vehicle ever built by humanity.
It really is an absolute monster of a machine.
It is. And, well, here is the thing that absolutely blew my mind when we started looking into this. This machine never truly stops.
No, it doesn't.
And it's not because, the operators forget to turn it off or because it's inconvenient to pause it.
Right, it never truly stops because stopping it incorrectly could literally destroy it.
Yeah, which is wild. So our mission today for this deep dive is to figure out why. We've pulled together this massive stack of sources, mechanical engineering manuals from the manufacturer, geotechnical surveys of the Hambach mine, operational logs.
A lot of really dense material.
So much reading. But I am struggling with a really basic concept here.
Okay, lay it on me.
When I turn off my car, or, I don't know, shut down a portable generator, I just turn a key or hit a switch.
Right.
The engine stops, the wheels stop moving, and that's it. So why doesn't a 14,000-ton machine just have, a giant, glorious red off-off button in the control cabin?
Well, see, that mental model, the car, the generator, even a standard bulldozer, assumes that stopping is simply an absence of power.
Yeah, you cut the power, it stops.
Exactly. But the Bagger 293 isn't just a machine that happens to be large. Its sheer scale completely rewrites the rules of physics that we just take for granted.
How so?
Well, for this machine, stopping isn't a power-off state. It is an incredibly delicate, highly choreographed transition. You're going from a dynamic, managed equilibrium into a stable, static condition.
A managed equilibrium.
Yeah. If you put a machine of that size to an uncontrolled halt under the wrong conditions, you aren't just looking at a stalled engine.
What are you looking at then?
You're looking at a scenario where it can literally sink into the earth under its own weight or buckle its massive steel conveyor structures.
Right, buckle its own structures?
Yeah, or shift so violently on its tracks that it just tears itself apart.
Oh, wow. So to pull off a safe stop, the operators have to manage multiple, completely distinct engineering domains at exactly the same time.
Right, it's a massive balancing act.
And before we even look at the ground beneath the tracks, we have to deal with the thousands of tons of actual earth moving through the mechanical veins of this machine at any given second.
Yes. To understand why you can't just, cut the power, you have to visualize the continuous flow of material.
The dirt it's digging up.
Right. At the front of the Bagger 293 is this bucket wheel that is 21.6 meters in diameter.
Which is, what, as tall as a 7-story building?
Exactly. And on that wheel are 18 individual buckets, and each one holds about 6.6 cubic meters of earth.
Okay, so from our notes, that is roughly the volume of a large cargo van, just to give you a mental image.
Yeah, a cargo van full of dirt.
There are 18 cargo vans strapped to a Ferris wheel, scooping continuously.
It's crazy. At full capacity, this machine is tearing 240,000 cubic meters of overburden out of the mine face every single day.
Hold on, I saw that word overburden all over the mining reports we reviewed. Is that just an industry term for regular dirt?
Yeah, essentially. It's the layer of earth, rock, and soil sitting on top of the resource they actually want to mine.
Which in this case is lignite coal, right?
Right. Getting that overburden out of the way is the bagger's entire job. And it doesn't just scoop it and drop it.
No.
No, that material is dumped onto an internal conveyor belt that runs down a 200-meter boom arm, and then it's transferred to a second conveyor on a counterweight boom, and then sent entirely off the machine.
Wow, so it is quite literally a river of rock and dirt flowing through the air.
Perfectly said. Every single component in that chain is dependent on every other component moving at the exact right speed.
Which means the shutdown protocol has to be incredibly deliberate.
Oh, absolutely.
Let's walk through what a planned normal stop actually looks like.
Okay, so first, you stop the rotation of that massive bucket wheel, which halts the actual excavation.
So no new dirt enters the system.
Exactly. But you have to leave the internal conveyors running.
Just to clear them out.
Yes. You wait while those belts carry every last ounce of rock completely off the machine. Only then, once the system is totally empty and the structural weight has returned to its baseline, can you finally power down the conveyor drives.
And I imagine that takes a while.
It takes several minutes, and you absolutely cannot rush it.
See, I keep picturing someone tripping over a power cord. What actually happens to the physical structure of the machine if the wheel stops and the belt stops simultaneously?
If everything just goes quiet.
Yeah, just an immediate halt.
Well, the thousands of tons of material that were in transit on those 200-meter belts just sit there.
Uh-huh.
And that introduces a catastrophic physics problem.
Because of the weight.
Right. The steel frame of the Bagger 293 is engineered to handle dynamic loading. When the belt is running, the weight of the dirt is constantly moving.
So it's spreading the stress out.
Exactly, spreading the stress across the entire length of the boom, which allows the steel to flex and rebound.
So the structure is strong enough to handle thousands of tons of dirt if it's moving. But if the dirt just sits there, it becomes this, like, localized dead weight.
Yeah, think of a suspension bridge, right? It's designed to have cars drive over it at speed.
Sure.
The structural tension is continuously adjusting. But if you suddenly park bumper-to-bumper traffic on that bridge and just leave it there for a week, the stresses change entirely.
Oh, I see.
The structural steel begins to experience fatigue in concentrated areas. For the Bagger, an abrupt stop leaves so much localized static stress on the boom arm that it literally exceeds the yield strength of the metal.
It would buckle.
You would absolutely begin to buckle. And you couldn't even attempt to restart because the sudden jolt of turning the motors back on under that massive static load would snap the belts or just shear the drive shafts.
Meaning you would have to send crews up there with shovels to manually clear thousands of tons of rock from a 200-meter boom before you could safely turn the motors back on.
Yeah, manual shoveling on a skyscraper-sized arm.
I can absolutely see why they avoid that at all costs. So, okay, let's say you follow protocol.
Right.
The wheel stops, the conveyors empty out, the drives power down, the machine is completely empty.
Safe and sound.
But now, that sheer mass introduces a completely different battle with the earth below it.
Oh, yeah. Now we enter the realm of geotechnical engineering.
Because the Bagger 293 doesn't roll around on perfectly paved asphalt or bedrock, right?
Not at all. It operates on the relatively soft, recently blasted overburden we were just talking about.
Yeah, looking at the schematics, this thing distributes its weight using 12 self-contained crawler units. They look like tank tracks, but, scaled up to the size of a city block.
They are massive. Each one is its own independent drive system. And the engineering magic here is that these tracks distribute that incomprehensible 14,200-ton weight so effectively that the actual ground pressure is only about 1.7 to 2.0 kilograms per square centimeter.
Which is wild. That statistic is wild to me. It means this gargantuan machine is exerting roughly the same pressure on the ground per square inch as a regular person walking in boots.
It's a brilliant design.
But from reading the geotechnical surveys, that low ground pressure seems a bit like an illusion.
How do you mean?
Well, it only works when the machine is perfectly positioned or constantly moving, because the ground under it is often completely saturated with groundwater.
Oh yeah, you hit the nail on the head. Soil mechanics at this scale is fascinating. The ground conditions are constantly shifting.
Right.
The earth beneath the mine isn't a solid mass. It's a matrix of solid particles and water.
It sounds a lot like standing on wet sand at the beach.
That's a perfect analogy.
Like, as long as you keep walking along the water line, you stay on top of the sand. But the second you stop and stand perfectly still, you start slowly sinking into the ground as the water gets pushed up around your feet.
Exactly. That is pore water pressure in action. And it applies perfectly to the Bagger. The water in the soil actually helps support the weight initially.
Okay.
But when you park 14,000 tons of steel in one spot, that sustained pressure starts squeezing the soil.
So the water has nowhere to go.
Right. The pressure of the water trapped between the soil particles spikes. Eventually, the water forcibly pushes the soil particles apart to escape the pressure.
Oh, wow.
And the soil literally loses its structural integrity. It's basically a slow-motion form of soil liquefaction.
So it's not a sudden sinkhole. You aren't watching it swallow the machine in real time.
No, it's progressive. But within just a few hours, a machine that was perfectly stable when you parked it can embed itself a few feet into the earth.
And I'm guessing you can't just, throw it in drive to get out of the rut.
Definitely not. If you try to restart and propel a partially embedded machine of this mass, the extreme torque required to push 14,000 tons up and out of a muddy depression, it's too much.
It would break the machine.
It can burn out the drive motors or snap the crawler linkages entirely. They literally have to bring in fleets of external equipment to excavate the excavator.
Excavate the excavator. That's amazing. Now, you mentioned in your notes that preventing this requires proactive ground preparation.
Yes, very extensive prep.
But how do you even compact ground for a machine that heavy? Doesn't the machine itself do the compacting?
Well, the machine does compact the ground, but in an uncontrolled way, which leads to that sinking we talked about.
Right.
To do it properly, operators have to plan exactly where the machine will rest way ahead of time.
They pick a parking spot.
Exactly. They bring in standard-sized heavy machinery, bulldozers, rollers, industrial compactors, to grade and compress a specific landing pad.
Oh, wow.
Yeah, and they set up drainage to divert groundwater away from the parking site.
Just for a temporary stop?
Well, if it's going to be a long maintenance stop, they go even further. They lay down massive interlocking steel mats to distribute the bagger's load even more, artificially expanding its footprint.
They are essentially terraforming a temporary foundation.
That's exactly what they're doing.
That is brilliant. You are building a custom parking lot for one specific vehicle every time you need to turn it off.
Yes.
So let's assume we've nailed the ground prep. The belts are clear, the landing pad is compacted, we've laid down our steel mats. The machine is resting peacefully.
Sounds nice.
It does. But going through the mechanical manuals, it becomes clear that it's not peaceful at all. Even when it's perfectly still, the machine is fighting an internal war against its own mass.
Yeah, the physics never sleep. We mentioned earlier that the Bagger 293 is dynamically balanced.
Right.
You have a boom arm extending 100 meters in one direction and a counterweight extending the other way.
Like a seesaw.
Exactly. When the machine is running, it relies on cyclic forces. The bucket wheel digging into the earth, the vibrations of the conveyors, the lateral forces of the machine sweeping side to side.
All those vibrations are good.
Yeah, all of those counteracting forces keep the structural health in check. They distribute the load.
Right. The machine is designed to flex. But when you stop, those dynamic forces just vanish, leaving just static dead weight.
Exactly.
If all that uneven dead weight is resting on the frame, isn't there like a central pivot point taking the absolute brunt of that stress?
There is. It is called the slewing ring bearing.
Slewing ring bearing.
It is this massive circular mechanical joint that sits between the crawler chassis on the ground and the entire upper structure of the excavator.
Okay, so it's the pivot point that allows the top half of the machine to rotate smoothly.
Yes, and it is engineered to handle unimaginable weight, but, and this is key, it is specifically engineered to handle that weight while it is rotating.
Ah, let's get down to the metallurgy of that. What actually happens inside that bearing when 14,000 tons of uneven static weight presses down on it for hours or days?
Well, inside that slewing ring are massive steel rollers, and they're sandwiched between two hardened steel circular tracks, which are called races.
Races, right.
When the machine rotates, the load is continuously transferred from one roller to the next. The contact patch between a cylindrical roller and a flat steel race is incredibly small.
Just a tiny sliver of metal touching metal.
Right. So when the machine stops, that entire 14,000-ton load is concentrated onto those tiny microscopic contact points.
It's all focused like a laser beam on a few pieces of steel.
And that causes a metallurgical condition called Brunelling.
Brunelling.
Yeah, the immense static load exceeds the elastic limit of the hardened steel.
Meaning it won't bounce back.
Right. The rollers are literally pressed into the races, causing permanent plastic deformation. They leave microscopic dents in the metal. And if you let that happen, the next time you try to rotate the machine, the rollers will catch in those dents.
It won't move smoothly.
It will grind, it will generate immense heat, it will shed metal shavings, and eventually the entire bearing assembly will just fail.
I read this detail in the operational logs and honestly couldn't believe it. To prevent these bearings from deforming, to prevent what are essentially metallic bed sores, the operators have to constantly jiggle the machine.
The metallic bed sores is a very vivid, accurate way to describe it, honestly.
It's so weird to think about.
It is. During an extended maintenance shutdown, the control cabin is never truly empty. Operators are required to follow a strict schedule to make small slewing movements.
Just moving the boom back and forth.
Yeah, they will rotate the upper structure just a fraction of a degree back and forth. They are shifting the machine's weight in its sleep.
Just rolling it over so it doesn't get stiff.
Exactly. By moving it slightly, they roll the bearings to a new position, which redistributes that static point load to a fresh section of the bearing race.
And that prevents any single contact patch from sitting under tension long enough to deform the metal.
Yep, it spreads the pain around, so to speak.
You literally have to care for it like a sleeping giant.
You really do.
But everything we've talked about so far, Clearing the belts, terraforming the ground, jiggling the bearings. That all assumes the operators have the luxury of time and a steady power supply.
Which isn't always the case.
Right. What happens when you lose that luxury? The final piece of this puzzle from our sources is the electrical system.
This is where things get truly violent.
Violent, okay.
Because the Bagger 293 does not have a gas tank. It doesn't run on a diesel engine.
Right, it's electric.
It runs entirely on high-voltage grid electricity. It draws massive amounts of power, up to 30,000 volts, through these thick, heavy trailing cables that literally drag behind it on the ground.
Dragging behind it, connecting it directly to the local power grid.
Yes.
I mean, running 30,000 volts through a moving vehicle in a dusty, wet mine environment seems inherently risky.
It's an engineering marvel that it works at all.
The manuals mention it uses variable frequency AC drives to run the machinery. Can you break down what that actually means for a layperson?
Sure. So an alternating current, or AC, motor speed is typically tied directly to the frequency of the electrical grid it's plugged into.
Okay.
A variable frequency drive is a complex piece of power electronics sitting between the grid and the motor. It takes the incoming electricity, changes its frequency, and feeds it to the motor.
So it's a middleman.
Yes. And by altering that frequency, the operators can precisely control the speed and torque of the massive bucket wheel and the drive tracks.
So normally when you plan a shutdown, those drives just slowly lower the frequency, easing the motors to a gentle stop.
Yes, it's a graceful ramp down. But if one of those trailing cables faults, or the local power grid experiences a sudden drop, or a critical safety relay trips, you don't have time for graceful.
The power's just gone.
Instantly,
Yeah.
the bagger loses its driving force, but the bucket wheel is still spinning with unimaginable momentum.
Oh, because it weighs so much.
Right. The machine has to execute an emergency shutdown before that uncontrolled momentum rips the boom apart.
But how do you even break a spinning wheel the size of a building? You obviously can't just drop a giant mechanical friction brake pad onto it.
Oh no.
The friction would instantly melt the brake.
A physical brake pad would shatter or catch fire in seconds. Instead, the electronics perform a maneuver called regenerative braking.
I know hybrid cars use regenerative braking, but how does it work on a 14,000-ton mining machine?
It's the exact same fundamental physics, just scaled up to a terrifying degree.
Terrifying is a good word.
An electric motor uses electricity to create a rotating magnetic field that pushes the mechanical rotor, turning the wheel.
Right, electricity in, motion out.
But a generator does the exact reverse. It takes mechanical rotation, spins a rotor through a magnetic field, and generates electricity.
Motion in, electricity out.
Yes. So during an emergency stop, the variable frequency drives instantaneously reconfigure the electrical state of the bucket wheel motors.
They flip them.
They turn those massive motors into massive generators.
Wait, hold on. You're saying they intentionally force the spinning bucket wheel to generate electricity?
Exactly.
Won't dumping 30,000 volts of sudden feedback completely melt the electrical system?
Well, if it had nowhere to go, yes, it absolutely would melt everything.
Okay.
The kinetic energy of that massive spinning wheel, hundreds of tons of rock and steel moving through the air, is forcefully converted into raw electrical current.
Right.
The magnetic resistance created inside the motor by doing this acts as an invisible, incredibly powerful brake.
I see.
That massive surge of electricity is then either shoved back into the local power grid, or if the grid is down,
Where does it go if the grid is down?
it is routed into giant banks of braking resistors.
Braking resistance.
Yeah, these are essentially massive coils of wire right there on the machine that turn all that electrical energy into pure heat.
Oh, wow.
They get incredibly hot, safely bleeding off the momentum of the wheel into the air.
So you are basically using the rotational inertia of the machine against itself.
Yes, fighting physics with physics.
But that sounds less like a brake and more like a calculated trauma to the internal gears.
Oh, it is. The forces involved in that deceleration are staggering. You are forcing a loaded bucket wheel to instantly sight against its own momentum.
Ouch.
The immense torque that hits the multi-stage gearboxes, the drive shafts, and the mechanical linkages during a regenerative stop. It is the absolute maximum mechanical stress those components are rated to survive.
It is a violent clashing of gears.
Extremely violent.
It sounds like throwing your truck into reverse while you're going 60 miles an hour on the highway just to use the transmission to lock up the tires.
That's a great comparison. It is entirely a brute force survival mechanism.
Does it work?
The emergency stop works. Yes, it halts the machine before it can swing out of control or, drop its boom, but it is not without a cost.
What's the cost?
Every single time the Beggar 293 experiences a sudden regenerative stop, the operational logs require a mandatory, rigorous inspection protocol.
They have to check for damage.
Extensive damage checks. Engineers have to physically go into the machine and meticulously inspect the gear teeth for bearing.
Wow.
They have to ultrasound the drive shafts to ensure the violent torque didn't twist or fracture the steel inside.
The machine survives the stop, but the trauma is very real.
Very real.
So looking back at everything we've pulled from these sources today, shutting down the Bagger 293 is this monumental synchronized feat.
It truly is.
It is taking a totally dynamic system and carefully managing its descent into a static state.
And honestly, it completely changes how you look at massive infrastructure.
Yeah.
You realize that everything is inextricably linked by the laws of physics.
Everything is connected.
Yes. A single decision about where to park the machine on the dirt dictates the pore water pressure in the ground.
Right.
The stability of that ground dictates how the steel structure rests. How the structure rests determines the static load on the slewing ring bearing.
And the metallic bed sores.
Exactly. The health of that bearing dictates how smoothly the machine can be restarted. And that startup sequence dictates how the electrical drives ramp up.
You cannot isolate a single variable.
No, you can't. It is one massive, interconnected ecosystem.
It just makes you respect the sheer brain power required just to put the thing in park.
Absolutely.
But before we wrap up this deep dive, I want to leave you, the listener, with one final intense scenario to chew on. Something straight from the engineering failure analysis that we really only barely scratched the surface of today.
Well, this is a good one.
We've talked about stopping smoothly, and we've talked about stopping violently due to an electrical loss.
Right.
But imagine this scenario for a second. The Bagger 293 is fully operating. It is sweeping across the Hampak mine, 14,000 tons moving in perfect, creeping unison.
And
Suddenly, just one of its 12 massive crawler units mechanically seizes.
the asymmetric failure.
Exactly. The track snaps, or a motor dies. The other 11 crawlers are still pushing with millions of pounds of force.
While one is dead weight.
Yes. How do the computers and operators instantly coordinate the remaining 11 asymmetric units to bring a moving, skyscraper-sized city to a halt?
It's such a complex problem.
If they brake too hard on one side, they skew the machine off its safe path. They could drag the boom over unstable ground, twist the chassis, and cause a catastrophic structural collapse.
It's a terrifying puzzle of vectors and leverage.
It really is an entirely different engineering nightmare to explore on your own. So the next time you turn the key in your ignition or flip the switch on a blender, take a second to appreciate that clean, binary simplicity.
I know I will.
Because out there in the German coal fields, there are no simple switches. There is no giant red OFF button. There is only the delicate, dangerous dance of keeping the laws of physics at bay.